let's move to lecture 5, Diffusion in Crystal Imperfections. So in previous lecture, lecture 4, actually, we put more efforts on how to obtain the diffusility in crystal, in grains. So, but for example, like the results we get is the diffusility equals to atomic jump rate times the mean square jump distance divided by 6 times the correlation factor F. So this is actually the diffusility of the diffusing atom diffused in grain or in single crystal. But if the sample, if your samples is polycrystalline materials, which means you have the grain and also in between two grain there's a grain boundary here, then how can we estimate or obtain the diffusility of the diffusing atoms? So based on this materials you are going to have, so let's take a look if there's a diffusing atoms here. So atoms probably will diffuse through the grain, then jump into the grain boundary and move along the grain boundary, and somehow probably at specific location it also jump into the grain. So the diffusing atoms probably jump in and out of the grain boundary and also jump in and out of the grain. So how to get the effective and how to get the diffusility of this kind of polycrystalline materials. So this is what we are going to learn in these lectures. So will be diffusion in crystal imperfections. Crystal imperfections included what? Included the one-dimensional defect is a dislocation. Two-dimensional defects, for example, like the grain boundary and free surface. We are going to show you how fast the atom diffuse in this crystal imperfection size. So in this lecture can be simply divided into two parts. The first part is going to talk about the grain boundary diffusion, and the second part would be talk about the surface and the one-dimensional dislocation diffusion. But in your textbook, actually spend more pages to explain the grain boundary diffusion, and just few pages to talk about the surface and dislocation diffusions. So let's move to the grain boundary diffusion. And in this part, you are going to learn we call the effective diffusility. So what is the effective diffusility? It's a measurable diffusility. You can measure the effective diffusility of your materials. Effective diffusility is you need to count the diffusility of this material. So you need to consider all possible diffusion paths for the atoms to diffuse in these materials. So in this case, we consider the diffusion in grain boundary or in grain, and also consider the diffusion in grain boundary, and need to consider the volume fraction of the grain and also the grain boundary. Then next, we are going to show you how to obtain or measure or get the concentration profile as a function of location and time in 3 different grain boundary diffusion mechanisms. So we are going to show you how to do that. So first of all, we need to we put more efforts on grain boundary diffusion. So diffusion in crystal imperfection. So before in lecture 4, actually we put more efforts on describe the diffusions in crystal or in grains, right? So when you try to draw the energy as a function of location to the atoms in crystal, so probably you will say you will have this curves, and this is the energy curves of atoms in the crystal lattice in grains. So if we have a diffusing atom here, and these atoms need to overcome the energy barrier, then it can make a successful jump to the other location with minimum energy, right? So this is what we learn in lecture 4. But if there are other diffusion paths of crystal imperfection size, such as dislocations, internal interface, that means if you have alpha and beta phase, then the interface between these two phases we call internal interfaces. Free surface means if your sample is a sheet of sample, then the top surface is a free surface. And on the atoms on the free surface usually is a dangling bond, right? So with a dangling bond, so it is usually the energy is higher than when the atoms locate inside the materials, and also the grand boundaries. So at least if the atoms locate at this crystal imperfection size, usually this size with higher energy and also belongs to metastable side. It means the higher energy. So for example, like higher energy means, for example, if we take the grand boundary as an example, when the atom locate at grand boundary, this site actually with higher energy than that in the crystal or in the lattice. So these atoms just need smaller energy, just overcome smaller energy barrier, then these atoms can make a successful jump to the other side. So that is the smaller migration energy, because now the atoms are at the site with higher energy. So this energy barrier is smaller than when the atoms locate at the crystal. So smaller migration energy means exponential minus smaller term. So the diffusion, if the atoms diffuse through grand boundary, must have a higher diffusivity. And higher diffusivity tells you that the grand boundary can be considered as a short circuit diffusion. That means the higher diffusivity that will spend a short time to allow this atom diffuse through the grand boundary. Or you can say the atoms diffuse through grand boundaries moving faster than that moves into the crystal. Okay, so then we are going to talk about diffusion in crystal imperfections. So we are going to show you the term which we call a characteristic diffusivity. What's a characteristic diffusivity? When we really talk about the diffusion in crystal imperfection side, you need to know some definitions for some special term. The first one is characteristic diffusivity. Actually, it means the diffusivity for specific path. So we call this kind of just for specific path can be the diffusivity for dislocation, diffusivity for grand boundary, or along the free surface. This kind of diffusivity, we call it is a characteristic diffusivity. And next is very important is you need to know the volume fraction of the crystal imperfections in your materials. So this means the capacity of available diffusion channels in your materials. So you need to estimate the defect density. Okay, so let's move to next slide. This slide is the characteristic diffusivity in crystal imperfections. Here, actually, we talk about included diffusivity in the bulk crystal, diffusivity in dislocation, and diffusivity along grand boundary and free surface. And the figure here, actually, the y-axis is a log diffusivity versus the reduced temperature, which is the melting temperature divided by T. So as you know, the difficility can express like this. So if you take a log and use a log D versus 1 over T, then the slope will be related to the delta H enthalpy term. Okay, so now you have this idea. And let's take a look here. This is a reduced temperature, so melting point divided by T. So, okay, sorry. So with you increasing the temperature, will be go this way. So if the temperature is highest, then this slope actually belongs to the facility in a liquid. And this is a melting point. So if the temperature is higher than melting point, our materials becomes liquid. So what you can get for difficility is definitely difficility in liquid. And if the temperature is below the melting point, then the material we talk about would be in solid, diffusion in solid. But diffusion in solid is not, we need to classify or categorize into different channels or paths based on different crystal imperfection size, which included the diffusion in bulk crystal, diffusion in DD is along dislocation core, or diffusion along grain boundary, or diffusion along a free surface. So if you fix the temperature at here, then you can observe what? You can observe the diffusivity in a bulk crystal is smallest, right? And the highest one will be diffusivity along a free surface. And in between actually is a diffusivity along the grain boundary and diffusivity along the dislocation core. And now we have a DD. The DD there are two different DD. The DD on dissociate means the dislocation. You can use the Berger's factor to describe the dislocation, right? So you can consider the undissociated dislocation means you have a complete dislocation. Complete dislocation. And what's a dissociated dislocation? Because your dislocation can be dissociated into two Berger's factor. Dissociate into two Berger's factor means dissociated one is a smaller dislocation, and this is complete dislocation. That means the dislocation is larger than this one, right? As long as this is larger dislocation, so that tell you the lattice distortion energy must higher than this one. So based on the energy side is higher, then you can expect that the energy barrier will be what? Smaller. So I can draw here based on the one we just described. And this is E, right? And this is a location, and we expected this is what we learn is XT is energy barrier diffusion in. Okay, sorry. Diffusion in crystal, we assume is that. But higher energy means what? I use the other color too. Higher energy means this. So this is higher. So the undissociated one with higher energy. So will be smaller migration energy. Smaller migration energy. So the diffusivity will be larger than dissociated one, because dissociated one means what? Smaller lattice distortion energy. Smaller distortion energy probably is smaller than this green one, so I probably here. So the migration energy will be larger than undissociated one. As long as the migration energy larger, then the diffusivity was smaller. Okay? Okay, so this is how the story. And this field, as we mentioned in previous line, the slope implying that what the enthalpy term. So the delta H actually is a slope here. It depends on the types of crystal imperfection. It involves the enthalpy term, energy term. So as long as you can get this curves, then you can know the delta H is what. Because as long as so how to get this figure? You measure the diffusivity, specific diffusivity at different temperature. For example, I measure the diffusivity inside the crystal at different temperature, or I measure diffusivity along the grain boundary at different temperature. Then I can plot this one. As long as I plot this one, you can get the delta H, right? And some people also do the approximation to use the melting point to substitute the delta H. Yes, some people do that. Because usually delta H, if the delta H is higher, then Tm is higher. So some people use this approximation. Okay, so this slide is going to introduce you. There are two commonly seen grain boundary structure. The first one we call it is a tilt boundary. The second one is twist boundary. For the tilt boundary, we can observe that we have a grain 1 and grain 2, and we have a grain boundary plane here. And the rotation axis is parallel with the grain boundary. And you can observe the theta is here. It's a tilt theta. So as long as on this the boundary plane, as long as you got a large number of edge dislocation, then you can observe the theta increase in the meantime. So the density of the edge dislocation on this boundary plane will determine the angles, the tilt angles. Okay, and the second one we call is the twist boundary. Twist boundary, you also have a grain 1 and grain 2, but you also have a boundary plane. But however, the rotation axis is perpendicular to the boundary plane. And the theta is depending on the rotation angle. And based on different theta, you can observe the different boundary structures. This is the example here is we have two different theta, so you can observe the boundary structure is slightly different. Okay, so let's move to the most important thing is we have a polycrystalline materials. Because the atomic jumping events always happens, some atoms diffuse along the grain boundary. Some atoms diffuse inside the grain and then jump into grain boundary and so on. And how to deal with, how to estimate diffusivity in polycrystalline materials. So that's what we want to discuss. And the first thing is very important thing is even these materials are polycrystalline materials, but the grain size, volume fraction of the grain and volume fraction of the grain boundary is different. So we can base, and for example, like a diffusivity for grain boundary, diffusivity for grain, right? And we need to consider the volume fractions of the grain boundary and the grain. Then we can estimate the average or effective diffusivity for these materials. So this is the idea, because for atoms either diffuse through grain or through grain boundary, but how much time it spent in grain and grain boundary will depending on the volume fraction of a grain and grain boundary, right? So the idea is something I just mentioned. So here this slide is going to tell you how to get or obtain the effective diffusivity in polycrystalline materials. So what's the effective diffusivity? you can measure the effective diffusivity is measurable. That means if you measure the diffusivity of your material, that means this kind of diffusivity is we call effective diffusivity, because it is a sum of all the diffusivity contribute from both for grain and grain boundary. So we assume the diffusion distance in a diffusion time t is much larger than the grain size s. So we assume this is dxLTD. dxL is a diffusivity in grain times the t larger than s squared. This is a diffusion length. Diffusion length is large than grain size squared. So this is based on what? Let me. Actually, the diffusion distance for square root of 4 dt, so we use dt. And as we pk this, and if you take a square, you can take a square. Something like this. So actually, like use okay, so it's so you use a dt larger than s squared, s to 2. So this assumption actually tell you what? Tell you that because during the diffusion length is much larger than the size of the grain. So that tell you one thing. Important thing is lattice diffusivity is not ignorable. So you need to, because the diffusivity in grain cannot be ignored. So at these conditions, we need to estimate the fraction of the time to the atom spent in grain boundary. So we call iota. Iota is a ratio between the time of the atom spent in grain boundary divided by the time of the atom spent in grain. So the time it is spent in either grain boundary or grain depends on the numbers of available jump site in grain and in grain boundary. So available jump site in grain actually you can consider as a valent of the grain boundary versus divided by the valent of the grain. So based on this concept, if we use a 3-dimensional as a model, then can draw this one. So if we have a grain here, so grain is S. So the valent of the grain is, because this is S, right? So it's a 3-dimensional case, it will be S to 3. But if you want to know the valent of the grain boundary, so it will be like this. This is delta, the thickness of the grain boundary. But if you want to know you use this, right? So it's S plus delta over 2 plus delta over 2 will be S plus delta and to 3 and minus the S3. S3 is the valent of the grain, so the rest of part will be the valent of the grain boundary. So because S is much larger than delta, so you can get the result will be 3 delta divided by S. So next we are going to get the effective diffusivity. So we need to sum the contribution from grain boundary and grain. Sum by what? By the distance, displacement, the total mean square displacement in grain. So will be a diffusivity times the real time to the atom to spend in grain boundary. So be a T is a diffusion time, and the portion of the atom spent in the grain boundary will be iota. And this is the mean square displacement in crystal will be the difficility of the lattice of crystal times the portion of the atom to spend in grain times the total time. So this will be the real, the exactly time spent of the atom to spend in the crystal. So you sum this up. So you sum this up. So you got the dB iota t and dx 1 minus iota t, and you got this will be the effective difficility times t. So and you can get finally you drop the t out, and you can get the difficility. Effective difficility can be expressed like a dxl difficility in crystal plus difficility of the grain boundary times the iota. Iota is the fraction of the time spent in grain boundary. Okay, so in order to know whether in your case you need to consider the extra term, because if your material is single crystal, the effective difficility will be directly equals to difficility in grain, right? Or grain in crystal. But if your material is polycrystalline materials, and probably you can use the TEM to measure the thickness of the grain boundary, the grain size of the grain boundary. But did we modify the difficility based on what? This term, whether this term is large enough to effective the difficility. So I give you an example here. Generally, the iota is much smaller than 1. Iota is less 1, much smaller than 1. For example, like the grain size, if the grain size is around 1 micrometer, delta is around 0.5 nanometer, so the order will be 3 order, right? 10 to 3, so it's 1,000 order. So this is 1 over 1,000. So if the dB is larger than dxl by 3 orders, then this extra term come from the grain boundary contribute from grain boundary will change or affect the effective difficility. So in this case, you need to modify the effective difficility as long as this is large enough. Otherwise, you can just use the dxl to estimate what you are interested in. You can directly use the dxl to represent the effective difficility. But some people probably will ask the next question would be, Professor, I have a material, but I don't know whether the diffusion path which diffusion path is a dominant diffusion path for specific material, for my material at specific temperature. How to know that? So my suggestion is you can measure the difficility at different temperature and draw the log D effective difficility over 1 over T. And depending on how many slope you can fit it in, then you can know how many diffusion paths exist in your material system. For example, if you take a look on this log D visibility, log D versus 1 over T. So if when you measure the effective difficility at different temperature, right, and you draw this, if you just get one straight line, that means within your interesting working temperature, only one diffusion channel, only one diffusion mechanism, one diffusion channel dominate or happens. I mean, your diffusing atoms just diffuse through just single diffusion channel. But however, if the curve is like this, for example, like this one, and then is a curve, something like that, and you can fit it by 2 straight line. That imply what? During your working temperature, During different temperature regime, the dominant diffusion path is different. So based on these results, you can, based on the slope you fitting, you can get a delta H, and based on delta H, you can expect it. This delta H is delta H because the different crystal imperfection site with different delta H, right? So based on the slope, you can roughly estimate what kind of diffusion path happens or involved in your materials. So this is how we deal with. Okay. So now next we are going to show you there are three different diffusion. There are three different diffusion patterns or regimes in polycrystalline materials. The first one we call it the A regime, B regime, and C regime. And within time t, and you can observe three different diffusion patterns of grand boundary diffusion. And the diffusion source is on the top of these materials, and diffusion direction is along these directions. And you can observe the A regime. Some people call it the all material regime or multiple boundary diffusion regime. Yes, you can observe the diffusions happens all along all materials. This we call the A regime, multi-boundary diffusion regime. And B regime actually, you can observe the diffusion happens, but the pattern is totally different with regime A, right? Because you can observe the diffuse along grand boundary and also diffuse slightly into the grain. So this we call a boundary regime or intermediate regime. And the regime C is different with the regime B, but similar, right? It's diffuse along the grand boundary, but you didn't observe the diffusing atom diffuse in to the grain, right? Compared to this one is some atoms diffuse into the grain. The diffusion distance is longer than this in this case. So we have three different diffusion patterns in polycrystalline materials through grand boundary diffusion process. But how to classify these three different diffusion regimes? We compare the dXL and dB, difficility in grain versus difficility in grain boundary. So for example, like for the regime A, multiple boundary diffusion regime, you can observe the diffusion length square root of dXLT much larger than S. S is the size of a grain. So you can observe the diffusion length is much larger than 1 grain size, because the diffusion happens across several numbers of size, the grain, right? So intermediate regime, you can observe the diffusion distance along the grain boundary is larger than S, because the diffusion happens across several grain. And also we can observe the diffusion happens inside the grain, but it's not diffused too much. So its S is larger than diffusion distance in grain. And this diffusion distance must be larger than lambda. Lambda we call it interatomic distance. Is in angstrom, in the scale of angstrom. But the regime C is what? The diffusion distance along grain boundary definitely is larger than 1 grain size. But 1 grain size must larger than lambda, interatomic distance, right? And regarding to the diffusion in grain, must very small, smaller than lambda. So you didn't observe any diffusion inside the grain. And some people call it regime B and regime C as isolated boundary diffusion regimes, because you can observe when I want to answer what's the concentration of diffusing atom inside this grain, you only need to consider one diffusion source. For limit properties, this one. So we call it as isolated boundary diffusion region. When you want to calculate the concentration of diffusing atom inside the grain, you only need to consider a single diffusion source. Then you can use the limited source cases we learned in lecture 3 to solve this equation. And we will talk about later to show you how to obtain the concentration of diffusing atom in B and C. Okay, so today let's end it here.